Hello, guys. Okay, today we'll be doing the machine learning, which is going to be part one on regression only. I'm going to show you now what are exactly the different parts of machine learning. We have, first of all, we have the supervised machine learning, which consists of regression and classification. And we have the unsupervised machine learning, which consists of clustering and dimensionality reduction. We'll explain this later on. Okay, the supervised machine learning is the regression and classification. Each one has its own model, okay, and some of the model they can share it together. We have the unsupervised machine learning, which is quite different from the supervised machine learning. And we have at the end the reinforcement machine learning, which is reinforcement learning, which is not going to be part of our curriculum, right? So we'll be focusing mainly on supervised and unsupervised machine learning. At the top of all the models, whether supervised machine learning and unsupervised machine learning, there's an umbrella. And this umbrella is called the skitty-learn algorithm. And underneath, we have all the models. We have skitty-learn, and we have exactly the supervised models, the unsupervised models, which is exactly regression, classification, clustering, and dimensionality reduction. Okay, and this is other model related to each section. The supervised machine learning is to have previously known results. What does it mean? We have the supervised, what you need to have exactly, you need to have an input, and at the end of the day, you're going to have an output, all right? If you code the supervised machine learning, we need to have first an input, and we're going to predict exactly what's going to happen. And we call this exactly the feature, first of all, the feature, and then we have the target. In this case, for instance, we have the feature that called exactly the independent variables, and the target is called the dependent variables. We have X and we have Y. And we'll be having like Y function of X. And F, it could be anything. It could be an algorithm. It could be a machine learning algorithm. It could be a function. It could be anything. All right. So we're going to see exactly the relationship between X and Y. This is an example here. It's an example here. So as I explained before, the machine learning, it can be regression and classification. We have an example here of regression. How do you know this is a regression and this is classification, for instance? If you see a regression, if you see a table or data like this, as you can see here, we need to have the axis, which is the temperature, the pressure, humidity, wind direction, and so on. These are variables which are exactly the features. I would like to predict exactly the wind speed. When you have data like this, wind speed, which is exactly the target, based on the feature here. Let me write something down here. What you have here, we have the axis and we have the y. Okay, and we need to have y, which is a function of axis. All right, we have x1, we have x2, we have x3, we have x4, etc. Or this is a multiple regression here. We have multiple variables here, okay, because we have many x's. Or we could have, for instance, another table, another data x and y only. So this one is going to be a function of 1x, okay? This one is going to be a function of x1, x2, x3, and x4. All right. When you have something continuous, when you have the y is continuous in this case, okay, it's continuous. It's numerical continuous data here. In this case here, we'll be dealing with a regression. All right. In this case here, you'll be dealing with a regression. And when you have something else, which is here, you have the x's. Sorry. Here we have the x's here, which is the gender, age, and salary. I would like to predict if this person has purchased or not. Okay, so this one is going to be pressures yes equal to 1 and pressures no equal to 0. So you have only two things. It's a choice. It's a classification. Like gender, male, female, is sick or not sick, is purchased or not purchased. So it's a choice. Choice could be a binary, like see in this case here is going to be 0 and 1, or it could be colors. It could be one color, two color, three color, etc. Okay, so the difference, please make sure you understand that. To understand if you'll be dealing with regression, guys, so you'll be dealing with the continuous numerical data for the target. Okay, and if you are for the classification guys, we'll be dealing with a binary or multi-binary data, but not continuous, not continuous. When you see data not continuous here, all right, you're in the case of the classification. If it is continuous, it's a regression. Okay, please, you need to understand that at least before you tackle any problem and you choose exactly the model. Make sure you understand you're dealing with regression or you're dealing with classification. So we'll be having an input, you're having an output. What do you want to predict? Okay, you're going to have the features, the predictors, the independent variables, which are the x's and so on, the attributes and so on. And here at the end of the day, we're going to predict exactly the response. And the response is going to be either this, the prediction is going to be this, or it's going to, in the case of the classification, it's going to be this. Okay, and in between, to move from one part, input to the output, what you need exactly? You need a machine learning algorithm. All right, you need the equations, you need the machine learning algorithm, you need a lot of stuff here. Okay, this is just an example here. An example here, you have a table, A and B. You have A, okay, we have A here, okay, and we need to predict, you need to have the relationship between A and B, which is exactly going to be X, and this one is going to be Y. And Y, F of X is going to be Y. Okay, and we plot exactly the B versus A. And you can see there is, okay, there's to some extent there could be a correlation, it could be linear equation. For instance, if it is linear, we can fit probably a line here. Is it good or bad? We cannot say unless we're going to calculate exactly the error. The smaller the error is, the better is the fit. Okay, maybe this one, it has an error 1. Okay, we're going to plot, we're going to do something else. We're going to plot something like this. Sorry, something like this. And maybe it has an error 2. All right. So if we, this one, if it fits, it's going to be, for instance, y equal ax plus b. And a is a slope here. If it doesn't, if the error is quite, if it is large here, we're going to fit maybe something called ax squared plus bx plus c. It's going to be like, to some extent, sort of a parabola. And every time, if this one it has an error 1, this one it has an error 2. If this one is smaller, then the model is this one, If this model is smaller, then the model is going to be this one. Okay, we're going to elaborate more on this. That's the principle, how it's going to work. In the case of a regression here, we're going to fit something, knowing the input and the output, we're going to fit an equation. Why we're doing this is for the predictions. Say, for instance, here, we have an A here. What's going to be here? The Y is going to be this one, or the Y is going to be this one. All right, we have two Ys here. So that's why exactly we need to be very careful here to select properly the model based on the error. Okay, this is just a principle, huh? This is just a principle. And the type of the models we're going to have, it's going to be supervised and supervised machine learning. But the most important thing, we are focusing today on the supervised machine learning, which is making predictions, and we need to have some labels. Okay? And the labels we're going to have is supervised machine learning. When it comes to supervised machine learning, we're going to have the discrete and the continuous. The discrete is for the classification, and the continuous, as explained before, is going to be for the regression. Okay, we'll talk later on about the supervised clustering, dimensionality analysis, and so on. Okay, so this is exactly an example here of continuous. Okay, because we have data continuous here, and this is an example for the unsupervised, which is exactly a clustering. This is cluster number 1, this is cluster number 2, this is cluster number 3. I want you from now to have an overview and understanding of how you, to some extent, of supervised and unsupervised. Supervised, it's all about making predictions, knowing the X and Y. Now we're going to plot X and Y, or Y and X. Okay, and we're going to see exactly there's a fit here. We assume there's a fit, and we would like to do some predictions. How to do some predictions? If you have the data point, any data point here, and from here to here, we're going to have the predictions, the Y predictions here. Now that's the X selected. Okay, so the data, what you're going to have the X and Y's. I'm going to see the correlation between the X and Y's based on the model chosen. Okay, an example of the regression here, guys, is an example of the regression here. We have a non-linear regression and we have linear regression. Okay, the linear regression is very simple. You have Y function of 1x only. Okay, in this case here you have the sales versus the TV. That's linear one. Okay, and a non-linear one, what you're going to have, for instance, Y is a function of at least, it's a function of X also, okay, but there's no linearity here. It's like a parabola. Okay, we can fit here a parabola here. Okay, unlike here is a straight line, and in this case here is parabola. This is non-linear, and this one is going to be linear one. It doesn't mean you have X and Y. It's going to be linear. No, it's not going to be linear. It could be non-linear. So we're going to see exactly the different approach how to resolve exactly this problem. First of all, when you plot it, you can see it. If you plot something like this and you get this one, you can see it's not linear. So we'll be looking for a non-linear model. If you see something like this, you can have an approach. You can tell, oh, there is a linearity here. So we're going to fit exactly an equation, something like this, AX plus B. I'm going to get exactly the A and the B's here. The A, what's A here? In this case here, is going to be the slope of this line. Okay, that's the slope of this line. That's A. And the B is going to be the intercept of this line. And the intercept here is going to be this one here. Okay, once you know the slope or the coefficient here, A, and you know the B, which is the intercept, then you can plot your line. That's a theoretical line. And the data here is experimental data. And every point here, every data point here, between here and here, that's theoretical, the predicted. That's the predicted here. And this is the experimental one. And you have error number 1, error number 2, etc. And the sum of the errors divided by the number of data points equal exactly the average error. Okay? When I elaborate this or more when we have some use cases. I'll explain this more in detail. This is in the case of a univariate. Univariate, what does it mean? It means only one x. This is a function y versus one x only. Okay, and this one is y versus one x only. For nonlinear and for linear regression, guys. All right. So this is an example here of a simple linear regression. We'll be having exactly this equation here, where beta here is going to be the coefficient, or going to be the tangent of the line. This one is the intercept, and this one is going to be the error. Okay, for multiple linear regression, okay, for the same, we're going to have what we're going to have here. We're going to have beta 1 x1, beta 2 x2, beta 3 x3. What does it mean here? If you have data here, you have y, and what you have here, multiple x. Multiple x, x1, x2, x3, etc. Okay, and y here is a function of x1, x2, xn. Okay, that's linear, very simple, and this one is multiple linear. Okay, so both models feature only a single response variable in the case of a simple linear equation. Okay, so we have what we have first. We have the intercept, and we have exactly the coefficient or the tangent. Okay, so and the most important thing to exactly is to calculate for every case the error, to make sure exactly your error is going to be very small. We cannot choose a model which has an error very big, so the prediction is going to be very bad. Okay, the model is chosen based on the smallest error. It's the bottom line. Okay, to make good predictions. And this is just univariate regression here. We have the independent variables. The independent variables are the x's. We call them the independent. The independent variables. And this one, the y's, we call them the dependent variables. Because these ones, they depend on this, on the x's. That's why we call them dependent and independent variables. Okay, keep this in mind. Again, univariate and bivariate regression here. We're going to explain the univariate. We have y and x here. You feed the line for the univariate here, and this one is going to be the intercept, guys, okay, as explained before, and this one is going to be the error for each data point. You have here an error 1, error 2, error 3, etc., until you get exactly the error. And here is going to be the slope, which is exactly the coefficient here, which is going to be W1 here. Okay, the W1 here. And the W0 here, in this case, is going to be this point here, which is the intercept. That's number one for the univariate. For the multiple variate, which is the bivariate in this case here, what does it mean? You have data, you have two x's, x1, x2, and you have the y. That's bivariate. Okay, bivariate, you have x1 and x2. What does it mean? You have two attributes. Okay, you have two variables here. Okay, so the y here is going to be a function of x1 and x2 only. And this is x1 and this is the x2 here. Okay, and you can see it's a plane, 3-dimension, and it's the y. The 3-dimension, you have something like this. That's y, that's x1, that's x2. Okay, here you have a line in this case, but in this case you're going to have a plane. Okay, and the intersection, and this one is going to be y is a function. It is, for instance, a x1 plus b x2 plus C. Okay, and C here is going to be the intercept. And the intercept in this case here is the intercept of the y-axis. And the intercept is going to be here. We're going to see more example, okay, and more use cases to explain exactly this. Okay, I want you first to understand, have quite a good understanding the difference between univariate, one variable, multiple variate, as many as you want. But it's going to be more complex. Okay, this is exactly the basic steps of the supervised machine learning. What we do in machine learning exactly, first of all, we're gonna load the different libraries, what we need for the libraries. The libraries we need. Don't load what you don't need. I'm going to explain in a use case what are the libraries needed. If we need a library to do some regression, basic regression, don't include other libraries, which we don't need. Okay, so, and then we're going to load exactly, this is for the library. We're going to load the libraries here. We're going to load NumPy, for instance, pandas. We need this all the time. This one has to be all the time. And here we're going to include the linear regression here, library, for instance. To include it from skilly learn.linear_model. Import this library. There's another library which we don't need. There's no point to include this. Okay? And the second one, we're going to load the data set. The data set, when you want to include the data set, you have to load the pandas. You don't need it. And as explained before, the load the data set, PD is pandas. It comes from here. Dot read CSV when you'll be dealing with CSV file. And here the name of the file itself. Okay, so you import this file from your path. Okay, and the next one is going to be we split the data into training and test data. So here we're going to split the data into training and test data. Okay, this is exactly, we're going to split the data into training and testing. The X are the axis of the data and the Y are the target of the data. So this is a feature, and this one is the target. And to split them, this is an algorithm we need. There's an algorithm called train, test, split. We split the data. If you have data, you're going to have to split it. In this case, we split the data into 25%. What does it mean? We take the training data, 75% we're going to train, and the rest of the data, which is 25% called the test data, is going to be tested. These are the unseen data, and we're going to see if the model can pick up this data or not. If the model cannot pick up this data, it's a bad model. If the model can pick up this data and can predict them, this is very good. Okay, so we start first for the X train, X test. I will explain this in the next slides. We have the Y train, we have the Y test. The model, that's the name of the model. We have to import it. And we have exactly test size, or we can put train size. With train size equal 75%. It could be, it's up to you here. But mainly, the rule of thumb, 75% to 80%, and here 30%. And the random state here, 42. If we redo exactly the same thing, so we said the random state is going to be exactly the same. Okay? To make sure we don't get other results. It's about replication of the result. Now, next one is going to be to train the model. This is the model we have chosen, linear regression. And this one is here. And after this, we set the model, the linear regression. and then we feed the model. We're going to do some fitting of the training data. X-train and Y-train. Okay, that's the fit. Why we do the fit? To get the best model. Yeah, okay, we do the fitting, and you see the fitting is going to be good model or bad model. And we do some predictions. And based on the predictions, we're going to see exactly if my prediction is good or bad. Okay, if my prediction is very good, then my model that I have chosen so far, the linear regression, is going to be very good. If this one is bad, then there's no point to work with the linear regression here. To conclude on that, we need to calculate something called the R-square. It's called the R-square score. That's the evaluation of the model. If the error, in this case here, if the error is very small, then it's very good. What does it mean? The Y test and the Y predict, they're very close to each other. If we have something like this, this dot here, this is Y test, and this one is Y predict. If this one is small, what does it mean? This one is going to be very close to here. Then my model is very good. If it is too large, the model is bad. Okay? And the R square here, the closer to 1, the better it is. I'll explain again this sort of quantities in use cases. When you see an example how it works, it will make sense. These are some of the 10 popular regression models. We have many of them, We have the linear regression, we have the GBM. In this case here, there's a GBM here, okay? We have the XBoost regressor. All of them, is regressor. That's why regression. We have the gradient descent regression. We have elastic net. We have okay? That's one. The number two, we have a statistical model, which is called OLS, okay? Which is statistical models, regression linear model, okay? So in this case here, before using it, if we would like to try this model instead of this one, for instance, we can, first of all, we can install it first, and then we can import, sorry guys, and then we can import the model, import stats.api as SM, statistical model. Okay, we're going to see again an example of that. All right, for the next, when you do some coding. And this is a process. You have to understand the process here, the way it works in machine learning. It's sequences. Okay, you have the data first, raw data. Then what you have next, we have to process this data. You do some cleaning, do some processing, get to the outliers and so on. Okay, get some missing value and so on. And you have to plot it. You can plot it here if you want, but we prefer here. Do some plotting here. It's up to you again. If you can plot it here, it's okay. At least you have an idea. But again, once you do the processing and data setting and so on, cleaning the data and so on, then you're gonna plot some data and see exactly what does it look like. Is it linear, non-linear? Okay, and then you do your modeling, you do the evaluation. That's what it is. I don't want to go further than that because this one, it comes later on. Tuning, communicating the result to the stakeholders, etc. Okay, so keep in mind, raw data, clean the data, plot the data, model the data. This is a process. Okay, and later on, it's going to be tuning the model, make it better. If the model is okay, make it better. If you get a model of, for instance, 85% here, then we'd like to improve it to 90%. And this phase is called the tuning. Okay. Now we're going to talk a little bit about the cost function. What is the cost function exactly? First of all, we need to have the correlation between the y and the x. Okay. And the cost function is going to minimize exactly the error. It's a way to minimize the error. To minimize the error is an iteration process. We start with something, and to minimize the error, we need to have to some extent the minimum function here. Okay, that's going to be the tangent of the function. That's going to be the slope of the function. Okay, I was going to tell you exactly if the process of minimizing the function here is an iteration process here. If this one at this stage here, we got an error equal, for instance, x1, and the next one is going to be x2. That's a guess to start with, and then x2, x3, until we get exactly here. At this stage here, exactly the perfect one, the error should be equal to 0, but never. It will never be equal to 0. Okay, but we need to find something. We need to have like a threshold. You accept an error equal to 0.001. You accept it. If you reach 0.01 here, then you stop it. You're very happy about this error. And this is called exactly the process called the cost function. Okay, and this process of cost function is based on the gradient. Every time we move from step to another step, until we get exactly what we want. It goes through every time we calculate the tangent here, until you get the tangent here equal to 0, because the tangent here is going to be equal to 0. But impossible to get the tangent equal to 0. Otherwise, it's going to take all your life to get a tangent equal to 0. All right? And here, this is exactly the mean square error for the linear regression here. And that's exactly your data. And that's the predicted one. Your data, your experimental data minus predicted for each data point. For each data point, and then the square, and this is exactly the MSE. And N here is the number of data points here of your data you have. Y, I is the actual value of data at point I, and the Y hat is the predicted value of the data at point I. And you do exactly 1 experimental here, predicted 2, etc., until you finish the last data. Okay. Here we show you exactly the cost function, how it goes. This is learning rate. If the learning rate is too small, it's going to take ages. Okay, if the learning rate is too small, like this, like this, like this, like this, it's going to take ages here to reach this. If it is too big, you're going to have this. You will never reach exactly the minimum. So we're going to have an average learning rate. For instance, 0.1 learning rate, it's okay to reach exactly the minimum we want exactly. And sometimes you have a cost function, you have a cost function not showing exactly this sort of curve, okay? But it's going to show you different curves like this. So you have two minimum here, one minimum here, and one minimum here. You have the local minimum here, and you have a global minimum here. We'll be looking at the global minimum. So this one is not the minimum of the function. It's one of the minimum. We'll be looking at the global minimum here. All right? So we'll be very careful what to choose first of all. Choose the learning rate, how much it's going to be. And where we going to start? Are we going to start from here? or are we going to start from here? It's very wise to start from here. At least we can reach straight away, quickly, the global minimum what we want. There's no point to have this, and this one doesn't give me exactly the error we want. The error we want. And we have exactly for the relationship between the continuous variables and other independent variables. Here we have an example of fitting exactly data points. These are the data points, and this one is the experimental one, predicted. Okay, and it shows you exactly, you're going to calculate here the sum of the different errors for each data point. And this one is calculated based on this. We have the one given, data given, and this one is calculated. This one is a way to minimize the residual sum squares. Residual sum squares. A here is going to be the intercept, and B is going to be what? And the B is going to be the slope. It's going to be the coefficient or the slope estimator. Okay. The same here, the metrics. We have three metrics. We calculate the R square. There's this R square metric. That one is for the model. If the model is very close to one, then the R square matrix, it tells you exactly this model is very good. If a model is 0.01, then the R square equals 0.01, then the model is bad. This one explains the model to other people as a percentage of the output variability. But the second one, the mean square error and the mean absolute error, is good to have this if you want to compare model number one, model number three, model number four, model number two, etc. Make a comparison between the models. But the selection of the models is based on this, of the R square, which is equal to this one. Okay, and the R square you can get from this, from skittle metric, import R2 score. And like this one, NSE, MAE, which is exactly the mean square error and the mean absolute error, you can, from skittle matrix, exactly the same, but you import mean square error and you import the mean absolute error here. If you want to compare, this one I use for comparison. And this one is for model selection, model acceptance. It is bad or good. Okay. We have talked about the residual here for each data point here. And the RSS, we covered it just now. That's the RSS. Okay. Again, we have talked about this, fitting the data point with a line. Here, we talked about these different errors here for the data point here. Okay. And here, how to assess exactly the goodness of fit. When you see data point, you have a fitting here, very good fitting here, and here it's the fit is quite strong around the regression here. When you see something like this one, the fit are very poor. Okay, so the quality of data and the strength of the relationship is what will determine exactly the fit. Okay, and there are many measures we can use to assess exactly the fit. Okay, and all this we have discussed before. Always is based on an error, based on the cost function itself. Now we're going to talk about the multiple linear regression. In the multiple linear regression, we have y function of many x's. Like this one, you have the y, which is a function of, that's the intercept. The beta are the coefficients, and the x's are the different data. We have x1, we have x2, x3, and this one is going to be exactly the error. That's all. So this one is going to be the matrix. Okay, and this one is going to be y1, which is equal to y1, y2, y3. Okay, and this one is going to be x1, different value of x1, x2, x3, etc. And here we have the intercept, beta 1, beta 2, this one, we have beta 1, beta 2, etc., plus the error. That's the way to resolve this equation. We are not going to resolve this by hand. We have already in our library how to resolve these equations here. I'm going to import some of the libraries to resolve for this equation. Again, we'll be saving this into use cases. Okay. An example here how this equation is unlike this one. This is yx, but this one is y function of x1, x2. This is x1, and this is x2, and this is a y. And this is the intercept. Okay. Cannot have an x3 here because it's impossible to plot it. We can plot it, but it's going to be very difficult to visualize it. But if you have an x4, is impossible, etc. Okay. So we need to have just some calculation. That's all, not enough. No plotting in this case. In the case we have 4 dimension, 5 dimension, and so on. Okay. Again, here there is a quantity very important. It's called the Pearson coefficient or the Pearson correlation. And the Pearson correlation here is a measure of the linearity relationship between variables and between variables. This is a relationship between variables. What does it mean? If you have x1, x2, x3, and you calculate the Pearson correlation between this and this, between this and this, between this and this, you can see if there's a correlation between these variables. And when exactly the Pearson coefficient here is going to be equal to 0, it does not necessarily mean variables are unrelated. We're going to see based on the range of Pearson, which varies from -1 to +1. If this one is Pearson here is -5, -0.5. What does it mean between x1 and x2? It's inversely proportional to some extent to each other. Between this and this, if it is 0.7, is positively related to each other. And this one is negatively related to each other. This is what it means exactly. Okay, but the range to some extent of Pearson is equal to -1 and +1. So the best way here, when you have something like that first, is again, always plot your data. Never interpret any correlation coefficient, whether it is linear or non-linear, without a plot. Okay, plot your data first. Very important here. Okay. So we have many coefficients. We have many coefficients, and one of them is Pearson. We have seen just now. Okay, we have seen just now Pearson. There's another one. It's called Spearman, and other for categorical data we have Kramerus, and we have categorical continuous data, something called point by serial. We focus now on the Pearson only at this stage because it handles linear relationship well. And there's something else for feature selection, because sometimes we have x1, x2, x3, and we have y. And you see that this one, for instance, is not well correlated to this one. It's very weak. It does not influence to some extent or affect exactly the quality or the quantity of y. But if you see this one and this one, yes, this one is very strong with this, and this one is very strong with this, and this one is very weak. So in this case here, this is called exactly, we get rid of this. And this is called the feature selection. Select which x's are good for y's. Otherwise, there is no point to use them. All right? An example here for the multiple linear regression, we have the size here, S, we call it S. We have the number of bedrooms, and B, with the number of floors, and F, and we have the age, A. All right? And we have the label here, which is exactly the target. And these are the features. We have the features. So we have F, a function, F, which is exactly the target, which is a function of the features. Right? For a simple linear regression, we have only one feature and one target. But in our case here, we have multiple linear regression. We have, so what we have here, we have the y, which is y here, or the label. Okay, we have y. It's a function of size, number of bedrooms, number of floors, and age of the house. Okay, and all this affects exactly the price of the house. Okay, so we need to have like a correlation. We need to have, for instance, y, which is a dependent variables, which is a function of x1, x2, x3, which is function of these, and these. And this one is going to be what? It's going to be what? The intercept, and this one is going to be the coefficient for each case. What does it mean here? If we beginning with multiple linear regression, huh? So what we have here, we're going to have y equal, for instance, 1.5 example plus 2.1 S plus 3.0 NB plus 10 NF plus 11.6 H. This is going to be what? It's going to be here the B0, which is exactly the intercept. And these one are the coefficients for each case, for each sort type of data. So the 2.1 is going to be this coefficient. 10 is going to be this coefficient. And the last one is going to be 11.6, which is going to be the next here. Okay. That was partitioning the data, splitting the data. As I mentioned earlier, we can split the data between 25%, 70%, or 30%, 70%, or we can split the data again. Training 65, validation and testing. And this one is going to improve the quality of the model. This one. You can do start with this one and you extrapolate to this one. So the training data is used during the development of the model. Very important here. The validation data can be used to improve the performance of the model. Very important here. And the test data is used to check the performance of the model with unseen data. Because the testing data are unseen. You remember when we have the testing data here, they are not involved in the development of the model or the validation of the model. It's later on when we feed the data, when we feed the model, and we do some predictions. So we're going to have some output. of data. Okay, this data we find here from the output is going to be compared to the test data. The closer this to this, the better is the model is. Okay, the better is the model. Okay, and then you're going to see if the model is very good. This is the unseen data here. This is an unseen data here. They're not seen by the model. If we get very small error here, then your model is very good. If the error is high, your model is very bad. Now we're going to do exactly the splitting here. And the splitting here is done randomly using a model we have seen earlier here. Where is it? Oh, sorry, it's a little bit further. Yeah, it's here. So it's here. That's the model. Okay, that's the model. It's called exactly test split, the train test split model. So we have to import it. We have to install it, or we have to import it straight. We'll show you this later. All right. And then what is left now? That's what it is. This is the original data. You'll be receiving data like this, with the X1, X2, X3 exactly, with the Y. That's the data, raw data you're going to have. Okay, and you're going to using the train test split. You're going to split the data. This is the, for instance, 75%, and this is going to be the 25%, and this one will be used as unseen data. And this one I use to develop the model. Okay, so the X train and Y train data I use to develop the model, and the X test and Y test I use for the unseen model. And you can see it here: train test split X and Y. This is the X and this is the Y. X is always capital, and the Y is always not capital. Test size, Y, or probably test size, or can have train size. It's up to you. Train size. Here, 0.75, and here, if you use the test size, it's going to be 0.25. And random, you can choose any number here. You can do 35, 45, for instance, any number, but keep it constant when you do it. So we have here the feature of the input. We have here the target of the input, which is X and Y. Okay, and we put the model. Okay, we import the train test split model algorithm, and we split our data. Now you have the full test to full data set. We split into feature and target. Okay, and then split this into training data set and testing data set. That's where it is. And we'll put this into the model. And with the use the test data later on to see if it fits or not. The model is good or not. In this case, for instance, as an example, we choose a linear regression model. We call it a regressor. You can call it anything you want. We call it whatever. Reg. That's it. And this is the model. Once you have the model, you fit the model and you predict the model. So first, model set, you feed the model, and then you predict the model. You predict with the model. This is exactly number 1, number 2, and number 3. We have the model, we have the fit, and we have the predict. And this one is going to give you exactly the predicted output from the model. And this value here is going to be compared to the test unseen, which is going to be this one. Okay? That's what it is. So this one here, y predict, when you do the prediction, is going to give you the y predicted, and you're going to compare it with the y test and see if this value are far from or equal or nearly same as the y test. And based on the difference between this one and the y test, we're going to calculate the error. If the error is acceptable or not. Okay? I think it's quite straightforward. This is exactly an example for the linear regression model. You can Google this and you can have an idea about what is expected to be between the brackets here. You can choose normal format here, as simple as possible, and then you can improve it later on. Okay? Another model is called the OLS, which is ordinary least squared model, OLS. It's mainly used for regression in machine learning, which is exactly a statistical model. It does exactly the same. There is no difference. We're going to see an example too. This does exactly the same. It calculates the y I minus exactly the same error. Okay, minimizing the error. And here we have the type of OLS regression you have. You have the one for the simple linear regression, you have a multiple linear regression, and you have polynomial linear regression. Polynomial regression, sorry. What does it mean? Here it's how you have the x1, you have the same x1 square here, you have x2 theta, cubic, etc. That's the difference. But here there's no power. Okay, there's no power on the variables x1, x2, x3, etc. But here you have x1, x1 squared, x2 squared, etc. Okay, x3 whatever, x3 cubic, etc. In fact, in most of the cases, we'll be dealing with maybe with a simple one or with a multiple linear regression. And this one could happen. Yeah, we'll see. Probably I will try to find something in the implementation of that to show you to you how it works. Okay, an example of that we have to see the predicting a car fuel's efficiency using based on its weight. So weight versus car fuel efficiency. That's one variable and one target. Okay, that's a multiple linear regression. We see predicting the patient hospital length of stay based on age, medical history, diagnosis case. Okay, so we have here 3 of them. Okay, and then we're going to predict exactly the predicting patient hospital length of stay. Okay, and this one here, polynomial regression example, we are predicting the price of a smartphone based on its features. For instance, a smartphone manufacturer employed polynomial regression to capture complex relationships between features and price. Okay, and many use cases for that. All right, and this is just an output of the OLS, which is exactly this one, which is the ordinary least square algorithm. You use it, you implement it, and you have, first of all, you have to import it, you have to install it and import it. Import it stats models.api SSM, statistical model. Right? We have TV, we have data, TV, radio, newspaper, and we have the sales. We have to predict exactly the sales based on these 3 variables here. So the sales here is going to be a function of TV, radio, newspaper. All right, we have 3 variables. 1, 2, 3. And what this is the output. And when you have something R squared here equal this quite high, close to 1, that means the model is very good, what you have done. This model, which is the OLS stats model, it's very good. All right. Or the adjusted R squared is the same, but still very good. Then they have the AIC. and you have BIC, and the AIC is a statistical measure used to the model selection in the context of regression analysis, particularly in linear regression. And it tells you here for the AIC, it quantifies the trade-off between the goodness of fit of the model and the complexity of the model. And this one, the lower it is, the better is the model. And the same for this one, the lower it is, the better is the model. And this one is good, is very good when it comes to the comparing some of the models. Okay, so you have to read some of this, very important here. You have to read some of this. It's an example of the TV. And here, what you have here, and this is the results. You have the radio, you have the TV, okay, and you have the newspaper, and you have the constant. This one, the constant here, which is 2.79 here, is the intercept. 0.04 is the coefficient for TV. This one is 0.18 is the coefficient for the radio, okay? And for the newspaper, 0.0028. You can see here, based on these three, you can see the radio has a stronger coefficient when it comes to the sales. Okay, because this one is the highest one. Okay, that's what it is. Okay, here it shows you only this the skewness and the characteristics of the different curves. All right, I hope it's okay. Please, if you have any question, I can go live with you if you want. I will answer exactly the question you're having. All right, thank you very much. I'll see you guys around.